We're going to hear from Armond. Armond Cohen is going to tell us about he'll be making the case for nuclear in the context of deep decarbonization.
Great. Thanks, Ryan, and I appreciate the opportunity to speak tonight. So I want to address two questions. I'll probably get to the first more than the second, why nuclear, and second, what nuclear. So let's start with the climate issue. The 195 nations met in Paris in 2015, and now we have an agreement in legal force which says we want to limit global warming to well below 2 degrees Celsius and pursue efforts to limit warming to 1.5 degrees Celsius. Well, what does that mean? It means a zero carbon energy system, and zero means zero. That's what the modeling says. For everything, electricity, we're going to talk mostly about electricity tonight, but also transport and industry, within 40 to 50 years as global energy demand doubles from increased wealth and development. What are our options to grow the energy system services by twofold, let's say, over 60 years and go to zero carbon? Well, they're basically four. There's reduce demand by efficiency. There's adopt zero carbon renewable energy like wind and solar. There's scrub the carbon out of fossil energy or from the atmosphere, sometimes called carbon capture and storage. And there's nuclear energy. Go backwards here, sorry. So the case I want to make to you tonight is that each of these options has challenges at scale. That's what makes it such a hard problem. As Ryan said, if we could do this all with one thing, then we'd be done. Let's start with efficiency. The first reality is we're probably not going to conserve our way out of this problem. Underlying demand for light, heat, and motion will grow as the world gets richer. We can mitigate that curve a little bit, but we can't eliminate growth. An example is 50 million new air conditioning units per year are sold in China. It's the most popular wedding gift in India. 5 million a year are sold in the U.S. The developing world is going to need lots of energy. You can make those units twice as efficient as American units, but there's still going to be growth. Nuclear challenges. Let's start with the fact that typically costs more than equivalent gas and coal. Slow to build. The best units are getting built still in 4 or 5 years' time. And there are public acceptance issues that Shirley's going to talk about in terms of accident risk, waste, and proliferation. Carbon capture and storage has challenges. First of all, it adds fossil fuel costs directly and via load to operate the scrubbing equipment, and you must construct and operate substantial underground pipeline and storage infrastructure. So everything has its issues. I want to focus on renewables in particular, partly because another panelist is going to go into this in deep and say that, at least it's my view, and my research leads me to the conclusion that renewables also have very, very significant challenges that do not make it a silver bullet. First, there's the fact that the direct cost of production is typically, in most cases, higher than fossil energy. Because the wind doesn't always blow, sun doesn't always shine, there is seasonal intermittency that can't be addressed by daily storage. We think of batteries as mitigating this problem, but in fact, these cycles tend to be seasonal. Finally, there's substantial infrastructure build-out required generation and transmission. The seasonal problem can be illustrated by these three charts. The two of them are for California, and what you see is, let's see if I've got the laser pointer here. This is the year on the x-axis, and you see that the capacity factor, the amount of energy that wind energy puts out, kind of rises pretty steeply towards the middle of the year, likewise for PV, but very, very low shoulders. Germany shows the same pattern for photovoltaics. This is June. The big orange bars and the little blue lines are January. So you can see like a 2 or 3-fold difference. So this is not a daily problem that's going to be managed by charging up a battery one day or half a day and discharging it the next. Wind is also highly correlated across continental scale. The wind is not always blowing somewhere, as it is often said. I mean, it is to some extent, but it also tends to be highly correlated. So low wind days in the east tend to be low wind days in the west. Battery storage is not going to solve this problem. This is a picture of Germany in 2050 at its 80% wind and solar goal. And you can see the blue line is daily load, yellow is deficit, what's not supplied by renewables, by wind and solar. You see overproduction on some days in orange, but in that particular month, this is October in 2050, there's still a very large need, the red line, for residual capacity. to provide that energy, and that's with storage. So essentially you need dispatchable, that is on-demand power nearly equal to peak demand in most of these seasons, in most of these studies, and seasonal storage, or you need seasonal storage capacity roughly in the same range as your peak demand. That's expensive and not easy to do. In addition, the scale of a renewable energy build-out, if we're going to do this all with wind and solar, for example, and you're going to hear an argument that we should, is very, very challenging in terms of just pure scale. To take one study, which actually is Mark's study, looking at the U.S. and trying to supply all energy from wind and solar, every state would have to build 22 of the nation's largest wind farms. Every coastal state would have to build 41 of the world's largest offshore wind farms to supply the energy. 1,200 times more central solar PV plants than exist today. Seasonal storage that's twice the size of the U.S. electric system, using technologies that have really not been demonstrated commercially at anything like this scale. And the ability to just basically turn off industry for 8-hour stretches when the wind isn't blowing and the sun isn't shining. I mean, that's the kind of assumptions you see in these studies, and I think they're great thought experiments because they tell you how challenging it would be to do all of this with renewables. If we do less of it, and if we have a mix of things, a lot easier. Also doubling the size of transmission. Is this doable theoretically? Maybe. Is it highly risky as a sole strategy in the real world to get to zero carbon? I would argue most definitely that we should not put all our eggs in that basket. That's been the conclusion of numerous studies from the Intergovernmental Panel on Climate Change, the United Nations Deep Decarbonization Study, the recent Obama administration's mid-century 80% carbon reduction study anticipates between a 2 and a 3 times or fold increase in nuclear. The wisdom, I think, of going forward to a deeply decarbonized world is that we need it all. We need energy efficiency, we need renewable energy, we're going to need some kind of decarbonized fossil energy for the grid, transport, and heavy industry, and next generation nuclear. But we need better nuclear, and Jessica's going to address this in detail. I don't know, do I have a couple minutes to? Okay, let me just tee this up, and Jessica's going to go in more depth. As I mentioned, nuclear has some challenges, no question. Cost, there is concern about safety, there are issues around waste, all non-trivial, and I completely put that out front. I'm encouraged because I see a generation of nuclear technology coming forward that essentially eliminates water from the equation using coolants with much higher phase change points, melt points, if you will. And what does that do? Why is that different? You know, basically, we've been using light water reactors for the last 50 years. Why does this make a difference? Well, first of all, there's the radically reduced accident risk and off-site impacts. If Fukushima, Chernobyl, and Three Mile Island all had a common denominator, which was the boiling off of cooling water. If you use something like molten salts or lead or sodium that have much higher, 600-700 degree phase change points, you're going to have less risk of accident and loss of coolant. Also, because you don't have a lot of water under pressure, you're operating more or less at atmospheric pressure. That eliminates the need for pressurized containment vessels. When you look at a nuclear plant, most of that is the containment vessel. The actual nuclear unit is very small. If you can take all that concrete steel out, which is about 2/3 reduction for these advanced reactors in concrete and steel, you reduce the cost and you shorten and make more predictable the construction times. There are 50 startups in the US, Canada, UK, and the EU that are all working on versions of this technology. We've taken a look at 12 of those companies and tried to cost where they will be. The current latest generation of light water technology, the so-called AP1000s being built in Georgia and South Carolina right now, are expected to come in at about $6,500 a kilowatt overnight costs. South Korea seems to be delivering units around the world closer to 3,500, although it's not clear exactly how reliable that estimate is. What the game changer here is the advanced units that we've looked at that come in on the high end at about $2,000 per kilowatt overnight, and on the low end about $1,500. So a big step change in cost. So my conclusion I want to leave you with is that more options are better and increase our chance of success. Nuclear should be among those options. You can look at more information that kind of backs up some of the things in my presentation at this website, and I don't know whether we're going to be sending the slides around. Thank you very much.
Thank you.